Everywhere you look, from biology to engineering, things are getting wildly, unbelievably complex. And our old toolkits, they're just not cutting it anymore. So, in this explainer, we're going to dive into some revolutionary new tools, a whole new toolkit that's giving us a fresh pair of eyes to make sense of it all.
All right, let's get right into it. Just think about it for a second. Our social networks, the global financial system, even the satellites whizzing over our heads. We're building these gigantic systems with millions, sometimes billions of moving parts, and we're generating more data in a single day than our grandparents' generation did in a decade. It's honestly mind-boggling. So the big question is, how on earth do we find the signal in all that noise? How do we start to see the hidden structure inside all that chaos?
Okay, so first things first, we need to get one really important distinction straight. A lot of us, we kind of confuse randomness with complexity. Think about a screen full of TV static. In a technical sense, yeah, that has a ton of information. It's totally unpredictable. But structurally, it's simple. There's no real pattern there. Now compare that to something like a living cell. It is incredibly organized. It's totally non-random. It's this meaningful, structured kind of complexity that we're talking about. And that's what demands a whole new generation of tools.
All right, so our first new lens, this one's a really profound shift in how we look at things. It comes from a branch of pure mathematics called category theory, and you can think of it as a whole new language for describing systems.
So what is it really? Well, in the simplest terms, category theory is the mathematics of relationships. Instead of getting bogged down in what things are, the objects themselves, it zooms in on what they do and how they connect to everything else. It's all about the arrows, the transformations, the connections between things.
And here's the absolute best way to think about it. If traditional math, the stuff based on set theory, gives us the nouns of a system, the things, then category theory gives us the verbs. It's all about the action. It gives us this really dynamic view of the world where the focus is on processes and functions, not just a pile of static objects.
Okay, I know this might sound super abstract, but it has some unbelievably practical uses, especially in complex fields like systems engineering. So let's bring it down to earth and see how it actually helps solve a real-world design problem.
Okay, so let's say we're designing a water system. Using category theory, you don't start by thinking about pipes and tanks. No, you start with the functions. You define an object for each requirement, like collect water, and another one for store water. And the rules connecting them, the design constraints, this part shall connect to this part, those become the arrows. What you end up with is a formal mathematical map of the problem itself before you've even thought about a single physical part. It's pretty amazing.
And this is where it gets really powerful. Because then you can map out different solution categories. So one solution might be a huge central dam. Another could be individual water tanks on every single house. Category theory gives you the mathematical language to map both of these totally different physical designs right back to that original problem map. It lets engineers formally prove that a solution actually meets all the requirements, compare them apples to apples, and even figure out how they might be combined. It's a game changer for complex design.
All right, let's move on to our next lens. So, if category theory is awesome for mapping out relationships we already kind of know exist, our next tool is all about discovering ones that are completely hidden. We're talking about finding the hidden shape of data, using a field called topology.
I want you to picture a massive, messy cloud of data points, just a swarm of dots. At first glance, it just looks like random noise. But what if, hidden inside that cloud, there's a structure, a circle maybe, or a sphere, or a few distinct clusters? How in the world would you even begin to find that?
Well, this is where the magic of topological data analysis, or TDA, comes in. It's a method that's brilliant because it's designed to ignore all the little bits of noise and focus only on the big, essential shape of the data. The classic analogy is you can squish and stretch a donut, but as long as you don't rip it, you can always tell it has one hole. TDA is what finds that hole, and that is totally revolutionary, because it lets us find relationships in data without needing to know what we're looking for in the first place.
So how does it actually work? Well, the basic idea is surprisingly intuitive. What TDA does is it takes that cloud of data points and it starts to slowly grow a little ball around each and every point. As the balls get bigger, they start to overlap. When they do, you connect their centers. And you just keep going. You track how these connections form bigger shapes, like loops or voids, as you change the size of those balls.
And this gets us to the core idea, which is called persistent homology, and it's just brilliant. See,
Features that are real, the ones that are part of the data's true shape, they're going to stick around for a long time as you grow those balls. They're persistent. But the features that are just noise, they'll pop into existence and then vanish almost immediately. So, when you plot it out, the long bars are your signal, your real structure. The tiny little short bars, that's just the noise you can safely ignore.
And believe me, this isn't just some abstract mathematical party trick. Right now, researchers are using TDA to analyze EEG data from the brains of kids with ADHD. And by studying the shape of those brain signals, they're finding these fundamental differences in connectivity patterns. It's giving us brand new insights into the disorder.
Okay, so we can map relationships with category theory, and we can find hidden shapes with TDA. But what about the big one? Can we actually put a number on complexity itself? Can we measure it? Well, our final set of tools is all about trying to do exactly that.
The theoretical gold standard here is something called Kolmogorov complexity, and the idea behind it is just beautiful. An object's complexity is simply the length of the shortest possible computer program that can produce it. It's like finding the ultimate, most elegant, most compressed recipe for something. Let's look at this table to see what that means. A string of all ones, super low complexity. The program to make it is tiny. Print the number 1 28 times. Easy. A repeating pattern like 1, 2, 3, 4, 5 is also pretty simple to describe. But a string that looks truly random, well, that's incompressible. The shortest program you can write to produce it is basically just printing the string itself, so its complexity is really high. Now, there's just one little catch with this beautiful theory. It's been mathematically proven that you can never actually be sure you found the shortest program. It's uncomputable. So brilliant idea, but not so practical.
And that brings us to a super cutting-edge and thankfully computable alternative, assembly theory. Instead of thinking about the shortest description, this theory defines complexity by construction. It asks, what is the shortest possible assembly line, the absolute minimum number of steps you need to build this object from its most basic parts?
And this is where things get really, really cool. The primary driver for developing this theory? It's astrobiology. The idea is that life produces molecules that are just way too complex. They have what's called a high assembly index, to have just formed by random chance in some primordial soup. So this could literally be a tool we use to detect life on other planets. We find a molecule with a high assembly index, and that could be a huge biosignature.
So, okay, we've got these incredible new lenses, but the final piece of this puzzle, the thing that ties it all together, is how all of this is being supercharged by artificial intelligence. We're talking about a whole new kind of partnership between humans and machines. This diagram really shows a completely new way of doing science. It still starts with that spark of human intuition. A mathematician has an idea. But then they can use an AI assistant to help formalize it, to search through vast libraries of knowledge for related work, and even to suggest pathways to a proof. It becomes this incredible partnership that just massively accelerates the whole cycle of discovery, from conjecture to proof.
So, to really make this future happen, there are a few key things we need to be doing. We need to keep pushing to get more mathematics into formats that machines can actually read and understand. We have to keep improving these large language models so they get better at actual mathematical reasoning. And this one is so important. We have to train a new generation of scientists and mathematicians to be fluent in working with these new AI partners.
And that really leaves us with one last big thought to chew on. These new lenses we've talked about, category theory, TDA, assembly theory, and combining them with AI, this isn't just about getting to the same old answers, only faster. No, this is about empowering us to tackle entirely new classes of problems, to see the universe in ways that were literally impossible before. So the real question is, when the machines can help us check our answers, what incredible new questions will we finally dare to ask?